Yeah.
Good morning. We're going to do molar volume of gases today, and what I'm going to show you is Avogadro's law and the combined gas law, which enables you to work out the molar volume of a gas. And then this afternoon we're going to do an experiment to work out the molar volume of butane. So, just going through a few questions on the worksheet. Before we do that, I'm going to just talk to you a little bit and remind you about a couple of laws. The first one is Avogadro's law. Avogadro's law says that 1 mole of any gas, now remember what a mole is. A mole is a number, and it's that big number, 6.02 by 10 to the 23. So it's a huge number because we're dealing with such small particles. So if you think to yourself, the word dozen is a 12, so a mole is just a number. So 1 mole of any gas occupies 24.5 litres at standard laboratory conditions. Now, standard laboratory conditions are 25 degrees Celsius or 298 Kelvin and 101.3 kilopascals, which is the atmospheric pressure at sea level. So that is a law that you have to remember. The other one you need to remember is 22.4 litres at STP, which is standard temperature and pressure. Standard temperature and pressure is 0 degrees Celsius or 273.15 Kelvin, and the same atmospheric sea level pressure of 101.3 kilopascals. So that's the law. It probably will be in your data book, but you need to know of it and how to use it. So we'll be using that. The other law we'll be using is the combined gas law, and that's where we're up to in our course. So the combined gas law I've just covered with you guys, and it was pressure times volume of a gas over the temperature. When you have those three together like this, it will equal the seconds. What am I trying to say? Pressure times volume over temperature is a constant. So once you have a second set of conditions, it'll be the same constant as long as you hold the number of moles constant. So you can change. So why we're going to use this is because we're doing our experiment at the conditions of our lab this afternoon. It's not going to be exactly 22.5 it's not going to be exactly 25 degrees Celsius this afternoon, and it's not going to be exactly 101.3 kilopascals. So what we do is we do our experiment, and then we use this to convert it into SLC. So that's one of the questions on here. I'm going to show you how to do it. Before we get started, if you have a look at your handout, it has a diagram of the experiment and how it's set up. So I'm going to explain that to you, and you might want to write on yours like I have on mine. So essentially, you have a conical flask, and in the conical flask, you have some HCl, hydrochloric acid. And if you have a look at the materials list, it tells you that it's quite strong. It's 2 molar, and you only have 10 mils of it. So I want you to use your imagination. There's your hydrochloric acid in there, and what you're going to do is drop some magnesium ribbon into it. Piece of magnesium ribbon, and it also tells you how much of that you have. So there's a table below your diagram on your worksheet that tells you exactly all the conditions and the data that I've written here. So you can see that it tells you the mass was 0.49 grams of magnesium. So I want you to imagine this. I don't know whether you've seen this experiment, but in year 10, there's the rule that you've learned with acids, and then one of the three is acid plus a metal, who knows, gives a given, always. What's the other one? Acid plus metal gives salt plus hydrogen gas, H2 gas. So if you've got a reactive metal and you drop it in an acid, it makes a gas, but it doesn't make any old gas, it makes hydrogen gas. So can you picture this? You're dropping magnesium into acid, it's going to react, and hydrogen gas is going to fill this part and then go up into here, and it's going to travel. Now this is a closed syringe at first, so it's pressed right up to there, and as the pressure of the gas forms, it's pushing it back, and this has a scale on it to measure how much gas is in there. Now you might say, well, it's not measuring all of this down here, but it is because there's air particles here. So it's the same volume because we know 1 mole of any gas occupies the same volume. So when this is generated, even though you've got some hydrogen down here, the air is the same volume. So you get a direct measure of how much in mils, how much gas through this syringe here. So when we do the experiment, if you were doing this one, we're not going to do this one exactly, this is an example. We know how much hydrogen gas that evolved from 0.49 grams of magnesium. So we're going to do these questions and it's going to take you through the process so that you can repeat it in the scenario this afternoon, which is a completely different setup because we're doing a different gas. So the first question there is write a balanced chemical equation for this reaction. And you can use this general rule down here, which you learned in year 10. So the first thing you need to do when writing a balanced chemical equation is write down the reactants. So you have hydrochloric acid. And you need to check the formula, but we know what hydrochloric acid is. But if you didn't, you check your periodic table, you know that hydrogen's +1, chlorine's in group 7, it's -1, +1 -1 equals 0, so that's right, hydrochloric acid, HCl, plus, so it's aqueous, it's in solution, mixed with water, plus our metal, magnesium in this case, it's a solid, and if you look down at the rule, it's going to make a salt and hydrogen gas. So you can write down H2 as a gas, and then if you have a look at, stand back, if you get your finger, in your case, and put it over where the hydrogen's coming from, you can see what's left. And the salt is a metal and a non-metal combined together. So you always write the metal first. So what is the salt going to be?
Magnesium chloride.
Yes, magnesium chloride. Very good. So you write that down, not worrying at first about the formula. Magnesium chloride. Then you get your periodic table and you have a look what group magnesium is in. And you can tell it's valency from there, so it's +2. Have a look at what group chlorine's in, and it's in group 7, so it's -1. So +2 and -1. How many chlorines do we need to neutralise a +2? 2? Yes, good. So it's MgCl2. So that's making sure all the formulas are correct. Chemical formulas, students get confused between a balanced chemical equation and formulas. This is step 2. Formulas are correct. Now you've got to balance the whole equation because what you have on your product side can't be more than what you started with. So you say 1 magnesium, 2 chlorines, only 1 chlorine, 2 hydrogens, only 1. You put a large 2 here. You need 2 of these. And that's a balanced chemical equation for this reaction. And you can't do the maths of this experiment unless you have the correct balanced chemical equation. So once you've written that up, it enables us to continue. So the second question says, convert the volume of hydrogen collected at the temperature and pressure measured in the experiment to standard laboratory conditions. So that's why we use our combined gas law. So this was A, this is 1. Question 2. You can see temperature at 20 degrees is not standard laboratory conditions, is it? And also the pressure of 101.035 is not, well, I haven't written it anywhere, but who remembers atmospheric pressure? What is it? At sea level is 101.3 kilopascals. They're going a little bit more accurate, so let's do that as well. 325 they're going to kilopascals. So that's the standard pressure, and that's what that's referring to, and it's also what it's in this standard laboratory conditions, the same pressure for both. Alright, so we're going to convert our volume of gas that we collected to the right SLC conditions using the combined gas law. Now if you're a bit confused, I'll show you how that works. So essentially T, this temperature here becomes T1. This is T1, I'll write it in a different colour so you can see. So this is our T1 here, and our pressure one is this, because this is what we did the experiment in. So this side of the equation is going to be the experiment, and this is the standard that we want to convert it to. So I'll just use another colour so that becomes a little bit more obvious. Experiment to standard. So down here, using the black, is that black? I put that in the wrong thing, there we go. The volume of the gas is V1. So you can see what we're going to do. We're going to convert these over. So who can tell me what T2 would be equal to?
degrees.
Yes, very good. Now we've never used degrees Celsius for these gas laws, do we? What have we got to convert it to? Kelvin. So we're going to add 273 to it. So what will that be? It'll be 298, is that right? No, that's not right, it's 25 degrees. What are we adding?
318.
293 Kelvin. Is that right? For 20 degrees?
Yeah, that one.
Yep, and sorry, what was this one?
318.
Should be 298 Kelvin.
What are we adding?
273. So what we're doing is adding 273 to it to make it Kelvin. You can be a bit more accurate and write 273.15 or sometimes 0.2, but we're just keeping it simple and saying 273.
Yeah, I mistook it and did 293.
Right. So that's very important. You're going to get the wrong answer if you don't convert your degrees Celsius into Kelvin first. Now, who can tell me what the P2 is?
101.325 kilopascals.
Yes, very good. 101.325 kilopascals is right. And then we only have one unknown, and that is the new volume at those conditions. So then we plug it in. So you can do that without even looking up here at the board. You do it, and I'll do it, and we'll compare answers. So starting with P1, we can rearrange this equation. Actually, I might do that. So V2 equals P1 V1 on T1 times by T2 and divided by P2. And that's going to equal P1 101.035. Should shut up, shouldn't I? You can leave this in mils or you can change it to litres. I might just leave it in mils. Your answer is going to be in mils. Times 5, T2. T1. Okay, what did you get?
I'm not sure yet.
I'll see if you got what I got. Really, I am remiss because I should put my units in and see that they all cancel and that you're going to get mils as your units, which is right, and it also reminds you what units you're in. But because we have a bit of a lack of space, I didn't put them in. So I could do that now while I'm waiting for you. So it'll be kilopascals here, and this is mils, and this is Kelvin, and this is kilopascals, and this is Kelvin. So you can see they're going to cancel, the Kelvin are going to cancel, and you end up with an answer in mils, so that's correct. And what did you get?
52.7.
52.7, fantastic. 4 mils. So you can see there's not much difference, but there's a little bit. This is saying, and you can check in your own understanding if it makes sense, because we are going at a hotter temperature. And what do we know about temperature and volume? Charles's law.
Isn't it the hotter it gets, the more volume?
Yes. So we've gone up a little bit in temperature. Has the volume gone up? So you go. That's a double check to make sure that your answer is right. You go, yes, good. All right, that's number 2. So we're getting closer to the answer. If you go to question 3. This says calculate the number of moles of magnesium ribbon. Going back to your stoichiometry days. You might have to go a bit closer, I'm not sure. 3, number of moles of magnesium. And I will use, rub off some of the board so that we can spread it out and use the other side. So number of moles of magnesium is, how do we work this out? Well, we have to look at our balanced chemical equation. So, into the colour, it's looking a bit messy, isn't it? Here it is. This is the balanced chemical equation. And this is the recipe. It tells us everything. So, the first thing we've got to do is look at the mole ratio. So you can see it's 2 moles to 1. And you have to then say to yourself, okay, I've got to work out which one's the limiting before I can use one or the other. So usually in these types of experiments, they've got more acid. So this one's the limiting, but how can you check? How can you check? So you work out the number of moles of each, and then you can see which one does not fall in that 2 to 1 ratio. So the first thing you do is this. So remember what moles is? It's mass over molar mass. So I'll just put a little reminder here. Is this blue? Yep. Moles equals mass in grams over molar mass in grams per mole. That's what we're doing. So the mass of our magnesium is 0.49 grams, that's a 9 grams, over, what does your periodic table say the mass is? So how many grams per mole?
24.312.
Yes. So we're just going to go to 2 decimal places, 24.31 grams per mole. And you can see the grams are going to cancel and you're going to get your answer in moles. So can you tell me what that is?
Uh, 0.02.
0.02 moles. Right. So now we're going to calculate how many moles of this is and check the ratio. So how do we do that, do you know? We've got a concentration. We've got a concentration, 2 molar. That means 2 moles per litre, but we don't have a litre. We've only got 10 mils. So how you work it out is moles equals concentration times volume. So it is 2 moles per litre times by, we have to convert this to litres of course, so it would be 0.01, 1, 2, 3, yes, 0.01 litres. And you can see you're going to get your answer in moles because the litres are going to cancel. So the answer is 0.02 moles. Is that right?
Yeah, that's right.
So you can see we have equal, hang on, is this right? I'm going to have to do, did I write it down wrong? Mass. I must have written it down wrong. Yes, I did. My mistake. But we could leave it as that. But in your data table, have a look. It's 0.049. I wrote it down incorrectly. But it doesn't matter. We can continue with this if you like. Or will we stick with? We better stick with what's on your notes for everybody else who's following. So 0.04, I made a mistake. There's a 0 there, which means there's a 0 here. Can't see for looking, and that means it's 0.002, and that's why I knew I was wrong. I was thinking what? 0.002. Because they weren't, for this example, they weren't going to be exactly the same as in moles. So you can see the magnesium amount of moles is way less than the moles of hydrochloric acid by a factor of 10. Up here, it's a 2 to 1. So you've got to have more hydrochloric acid than you do magnesium, which is absolutely right. But which one's the limiting reagent? Which one's going to run out first?
Magnesium.
Yes, because all we need of the hydrochloric acid is double that, isn't it? We need 0.004. We've got 0.02. We've got a massive amount of hydrochloric acid. Can you see that? So this is the limiting reagent. And why do you need to work out the limiting reagent? Because we're trying to work out the moles of hydrogen formed, and we have to use the limiting one, the ratio of the limiting stoichiometric ratio of magnesium to this. If we use this, we're going to get a false amount because this runs out before this is run out. So we have to use this mole ratio because this is in excess. So it says for 5, what reagent is in excess and which is the limiting? So you've answered that one, and you're happy with that?
Yeah.
Is that okay? Everyone's up to where I am? Yeah? And then 6 says, calculate the number of moles of hydrogen gas produced. Right, we're going to do a new board. So, we're up to the sticky end now. We're going to work out the number of moles of hydrogen gas. And you're getting close to the molar volume. Number of moles of the product, hydrogen gas. So, we've got our ratio. I'm just going to rewrite it. There's 2HCl aqueous plus magnesium goes to MgCl2 plus H2 gas. Have I got that down right? Aqueous. And we know this is the limiting reagent, and we know how many moles we had. Who can tell me how many moles we had? Moles of magnesium.
That was 0.002.
0.002 moles. So, note the communication. Very important in chemistry that you do this type of communication, otherwise you write numbers everywhere and no one can follow what you're doing. So moles of magnesium, we're going to use this recipe up here. This says 1 mole of magnesium, because remember that a balanced chemical equation is a mole ratio. 1 mole of magnesium gives 1 mole of hydrogen gas. So therefore, moles of H2 gas is, what is it? Say it.
Yeah.
Yeah, 0.002 moles. And now once we have the number of moles, we can use Avogadro's law to work out the volume. Yes? So, going to the next question, so we're keeping you on track here. It says, calculate the number of moles of hydrogen gas produced. And then calculate the theoretical volume of hydrogen gas produced at SLC. So, we know, what do we know? Avogadro's law says it's 24.5 litres per mole of gas. But we don't have 1 mole, so it's not going to be 24.5. It's going to be a fraction of it, isn't it? So, you can use your units to determine what to do. You want your answer in litres because we're trying to work out the volume of your H2. So it's going to be 24.5 litres because that's at SLC, standard laboratory conditions, times by the number of moles, because this is litres per mole and this is number of moles, 0.002 moles. Your units are going to cancel, and you see you'll get your answer in litres. And what is that?
.049.
0.049. What was the next one? Was it exactly 0.0? Oh, exactly. Okay, litres. And then we can convert it back to mils if we wanted to. So we're saying it's 49 mils. That's the theoretical of what we should have got. Did we get that when we did our experiment? What did we get? Who can remember? It's on your sheet.
0.004.
No, how many mils? How many mils of hydrogen do we measure?
10.
With the syringe. With the syringe. Mils of hydrogen produced. This is hydrogen, remember? How much was in the syringe?
52.
Was it exactly 52? 52. Let me have a look. I'm looking at that table if you're wondering. So, volume of, yes, 52. So, what you've got here is the theoretical. Because we've used an equation to work out how much hydrogen would be produced from a certain amount of magnesium. So, thus, the theoretical volume of hydrogen produced, hydrogen gas produced, is 49 mils. But the experiment, this is unusual because normally the experiment is less than the theoretical. However, the experimental value, how much we got in the experiment, as measured by the syringe value, as measured, I hope you can read this, by the syringe, is 52. So where are we up to now? It says, this is steps it out nicely. So calculate the theoretical volume, we've done that. What is the percentage yield of the gas produced? Percentage yield. In this case, you'd want to do the percentage error. I know it says percentage yield. I'll do both of them so that you know how to do both. You can do the percentage yield or the percentage error. If I was a student doing this practice, I'd want to know what my percentage error is. But let's do, so percentage yield is equal to theoretical, hang on, I'm doing error. I don't think that works, do you? Oh, I could press hard enough. Or maybe I'm using the wrong side. I don't know. Percentage yield is the experimental value, mental value over the theoretical value times 100. So, in this case, which is most unusual, we've got a bigger amount than the theoretical, times 100. What do you get? We got more than we should have got, so it should be over 100%.
106.122449.
106.12?
Yeah.
12%. Very unusual. And what you would do from here, and I think it asks you, is you explain why. And there's lots of places that in the experiment could have been errors like the weighing of the magnesium. The fact that, well, some gases get less, so it's very unusual that it would be bigger. Instead, you can do the percentage error, and I'll show you. You should write these down because they never give these to you, these particular formulas. They expect you to know it off by heart yourself. So there's one for you to remember, and the error is very similar. It is equals theoretical value minus experimental value and that's in these straight lines. Do you know what they mean? Straight lines around something?
It means that if it's a negative, when you take it out of the lines, it's positive.
That's right, it's called absolute value. You take no notice of the negative sign. Absolute value. I'll just write that in another colour so you can remember. This is called the absolute. So it doesn't matter about the fact it's going to be negative in this case, all over the theoretical value times 100. I'm sorry, I've run out of room. Multiplied by 100. That goes in there. And if you do that, tell me what you get. So it'd be 49 minus 52 over 49. No, what's the, 49. Theoretical value is 49.
6.12.
6.12% error. That tells you how much error, which is normally what you want to know in your experiment. You can see that I could have just taken 100% off here and we would have got the error. And that's how you find error, or vice versa. You take them away from 100%. So it's 6.12% error. So, number 9 says, suggest errors to account for why the percentage yield may not be 100%, up here. And also, it doesn't ask you this, but how come we've got 6% error? And you just have to come up with a number of plausible reasons. And when students only give one, they're not going to get full marks. So there's quite a lot of experimental error that could go wrong in this, can't you see from that setup? You remember? Like, let's just keep it running, it's okay. If I get this out, I'm going to hit this nightboard. If we go back to the diagram, you can see that in this setup, it wouldn't be perfect, would it? Because what you've got to do is take the cork off, drop the thing in, and quickly shut it. But in that case, you're more likely to lose gas, which this is showing you're getting more gas. So that's unusual, as I was saying. But so you could say things like the mass of the magnesium perhaps wasn't weighed to enough decimal points, that might have been restricted by the calibration of the scales themselves. You could talk about the fact that the hydrochloric acid may not have been exactly 2 molar. The concentration might have been slightly different than that. So those are two main things. Then you can talk about the fact that there might have been some leakage in your, well, if it was leakage, you'd get less gas. So no, you wouldn't talk about that. It makes it harder when it's above, and it's very unusual that it is. You could say perhaps that, what else could you say? No, that's probably all you could say when it's over. That shows you understand, because if it was under, which is much more likely, you could say all the two things I've already said, and then you can say there was leakage in the syringe, and you could also say you lost a bit of gas when you put the magnesium in because you couldn't shut it in time. So, and that's it. Are there any questions to do with that? So I think we haven't actually finished the, we get the molar volume of this. 1 mole would have from our experiment. So what we can do now is I'll show you how to get the molar volume, because that's what it was all about. I'll just move this out again. It's a bit funky. Bit of gymnastics involved here. Right. So the volume of 1 mole is what we're trying to prove when we do this afternoon's prac. And we know that if we had exactly 25 degrees over there and it was atmospheric pressure at sea level, we would get 24.5 litres, wouldn't we? Theoretically. So that's what we should have got. So let's see if this value converts to, that's our experimental value, say if we did this experiment ourselves, let's convert it. How do we do it? We use the combined gas law. So let's do it together to see, because this is what you will be doing on your worksheet. I'll just rub out some of this so I've got some room. If I can rub it out. Doesn't rub out very well. I don't like that one. Maybe this one. So I can edit the video. So, wow. We don't want to be doing that too often, do we?
I'll fix your first one.
So, no, it's okay, Libra. So, let's just write down our data. So tell me what the combined gas law is.
Pressure times by volume divided by temperature.
We need little subscript.
They're all one.
Pressure
One. Yep.
Equals pressure 2 multiplied by volume 2 over temperature 2.
Beautiful. So we want to convert our experimental value as if it was perfectly in, this is what you'll be doing. So this afternoon you'll be collecting butane gas and measuring its volume, and then you have to convert it into SLC or STP. So you use this. So what's our pressure from your experimental table? What was the pressure? It was P1. So we're working out molar volume. Molar volume of the hydrogen gas from our experimental data.
So pressure was 101.035 kilopascals.
101.035
kilopascals.
Yep, times by the volume, which is 49. 49 over, what was the temperature?
293 Kelvin.
293 Kelvin equals P2. That's what we want it to be. So are we changing it to STP or SLC? Do you want to do STP instead? Yeah? So if we're using, we want to know the molar volume of hydrogen at STP. What am I going to put in for pressure? Do you know? It's the same for, doesn't matter what, SLC or STP. What's the pressure?
101.325
Yes.
kilopascals.
Yep. Times by, well, we don't know, we want to know what our V2 is, over our temperature in Kelvin at 0 degrees Celsius. What is it?
298.
That's 25, 0 degrees Celsius.
273.
Yes, very good. Let's just leave it as 273. So now we just have to rearrange this. So you get V2 equals 101.035 times 49 divided by 293 times by 273 divided by 101.325. And what do you get? It gives me time to rub this off. It's funny. Not really. You've got to have some comic humor in the video. Alright. There's the room. So we're going colder, so essentially it should be a much lower volume. Anyone got an answer for me? I haven't got any.
45.52
milliliters, yeah. Because we had our, this is in mils. So this is going to be in mils. So that's less, isn't it, than 49? That's how you check. It's got to less that now. That is milliliters per how many moles did we have? That's not per mole, is it? How many moles of hydrogen gas did we have?
0.002.
Yep, 0.002 moles. So we'll get it per mole now, once you divide that, because that's what we're trying to do, the molar volume of hydrogen gas, which should be 22.4 litres, but we'll see how close we get. What do you get?
Oh, unusual.
22,601
226. Yeah. Milliliters per mole. Good. And when we change that to litres per mole, divide by 1,000, it's 22.61 litres per mole. That's not too far away. That's pretty good, isn't it? This is the molar volume, experimental molar volume of hydrogen. It should be 22.4. We got 22.6. What is the thing that we should do now? And you'll be doing this afternoon. Once you get your value, it's not exactly what should you do. What's the next step? Percentage error. Yeah, and you know how to do that. Who can tell me what it is? I'll write it out again. Percentage error equals
Theoretical value minus experimental value
theoretical minus experimental
in the absolute value brackets divided by theoretical value times by 100.
Yes, so let's do it. It's going to be 22.4 minus 22.61 all over 22.4 times 100.
Sorry, 220,261. I think I got that wrong.
I got negative 0.9375.
And don't worry about this, it's in absolutes.
Yeah.
So what is it?
0.937.
No? Have you times by 100?
Yeah, I do.
Yeah, that's not much error. Good. Excellent. So if you got that this afternoon, you'd be pleased, wouldn't you? If you got an error trying to prove Avogadro's law, which is what you're trying to do this afternoon when you do it as well, trying to prove Avogadro's law of working out the molar volume of a gas. In this case, we just used what we had to work out the molar volume of hydrogen gas, and we got that much error. That's good.
It's actually 0.938.
Oh,
So you got it there. Yeah.
Oh yeah, because it's 500.
938%. So, any questions?